everyone. So this is the problem of the day for GFG. So this is the second time me recording this video. First time I did not turn on the audio. So burning tree. So burning tree it's a very important as well as very informative question you can say, because in this we'll get to know a very important concept in trees in general, you can say. Binary tree, a target node is given for you. Determine the minimum time required to burn the entire tree. The target node is set on fire. 1 second. In 1 second, the fire spread from a node to its left child, right child, and its parent. Okay. The tree contains unique values, and the time complexity is big of n, and this space complexity is big of h. So let's take this particular test case to understand the problem statement even further. So target node is this. So at time t is equal to 0, this is burnt already, or this is burning, you can say. So at time t is equal to 0, it can spread to its parent, it can spread to its left child and to its right child. At the same time, simultaneously it will spread. So it will spread here, spread here. At time t is equal to 1, t is equal to 1 and t is equal to 1. From here, we can say that we are using BFS and not DFS. Because if we use DFS, it will go for left and it will continuously go for left until and unless left exhausts, like left is equal to null. Till we don't get null, we just keep on going to the left, which we don't want. We want everything happening simultaneously. So we'll do BFS calls, BFS traversal. So okay, at time t is equal to 1, this and this have been burned. So at time, okay, we'll take this one. It doesn't have left, it doesn't have right. The parent is already burned. Can we burn an already burned node? No, we cannot. So it it will not go any further. This it will be contained here. So here simultaneously, left is not there, right is not there. This is already burned, so it will be contained here. Here, if you can see, left is burned, parent is not there, right is not burned. So this can burn. So at time t is equal to 1, this is burning, and this will start at time t is equal to 2. As stated in the question, it will take 1 second to burn. So at t is equal to 2, we are here. So after that, we'll check if the parent is already burned, so we cannot burn it again. We'll go to the left. Left is not burned, so we have to burn this. At time t is equal to 3. And we'll check the right. Right is also not burned, so we'll burn this as well. So time t is equal to 3. 3, how will 3 come? 2 plus 1, simple. 0 plus 1 is 1. 0 plus 1 is 1. So because we need 1 second to burn the node. So we'll check how we can do this. So here the main problem that we face is getting the parent node, because if you are standing here, we already know what is this. We already know what is this. This is root dot left. This is root dot right. But this is not root dot parents. We don't have any parent node to any node, to any particular node. We don't have parent pointer, you can say. So we have to create parent pointer, or we have to store it somewhere so that we can able to access the parent of 2, and we'll get a unique value which is 1. So for getting unique value, it has already stated that the tree contains unique values. So we don't get any contradiction. So for that only this constraint was given. If this constraint was not given, then this problem would have been even more hard. So this is hard, and If this constraint was not given, it would be even further. So for that, now the question is, how do you get the parent? So we can do a simple technique. As we know that every value in the tree is unique, can we store it in a hash map so that we know the node comma its parent? And if we call for node like map.get for node, will get its parent. So this is very important in this particular question, because if you don't get this idea, then you cannot solve this problem. So suppose we are here. So parent of 2 is 1. Parent of 4 is 2. Parent of 5 is also 2. Parent of 3 is 1. Parent of 6 is 3. Parent of 7 is 3. So whenever we need parent of 7, we just go to map and we get 7. So it will directly return you 3. From that, you can just go and burn this particular node. But here, one problem that we face is that, let's suppose we are here. At time t is equal to 0, we are here. We'll burn this one left, burn right, and we'll burn the parent. So at time t is equal to 1, we are here. At time t is equal to 1, we are here. At time t is equal to 1, we are here. So if we are here, left will check it's not there, right will check it's not there. But how do we know that this parent is already burned? So for that we use a visited array. So this is very common in graphs, and this also, we can say that this is also a graph problem if you convert it, because graph can go to its parent also. Undirected graph, it can go to its parent also. So we can see the similarity between this question and a graph, this, as well as we are going to the parent, and that is also one similarity between this question and the graph. And we know that every tree can be a graph, but not every graph can be a tree. So we'll do a dry run, the complete algorithm dry run for this particular test case. So first of all, we'll go and make a hash map which will contain all the parent of each one. So one will contain nothing, null. Two's parent is 1, three's parent is 1, 7 parent is 3, 4 parent is 2, 5 is 2, 8 is 4, and 10 is 5. So this is the first part of the problem is done. Then we have to find the target, which we'll do while we are doing this stuff. I'll explain you when we are doing the code. I'll explain that. We'll find the target because this is an integer value, and we cannot go left, right, and parent for an integer value. We have to find the node of that particular target. So we'll find that node while we are making the hash map, and we'll get but this node. So in this node, at time t is equal to 0, this is burning. So we'll find the left, not the right, not the, and we'll do the parent call. We'll get the hash map. We'll make a call to hash map, and it will give you 5. So we'll make a queue, because in BFS, as you know, we'll store queue. But storing the node value is not enough. We have to store the time as well, because we have to pass it to other node. We have to know that time is equal to 1 here to make time is equal to 2 here, because if we don't give, then we don't have any time value. So we have to make two things, that is, one is node value, or you can say node, and the other is time. So for that, in Java you can make a class pair which will store two value, which is the current node and the current time. So we'll make a queue. Firstly we'll add the pair, the target node, and time t is equal to 0, because At target, always the time is equal to 0. So we'll we'll do the left call, right call. It's not there. We'll do a parent call. Parent call is there. So first of all, we'll remove the top element from the queue, and then we'll burn this. So 5 and t plus 1, because this is burning at t. So this will take time t is equal to 1 to burn. So 1, and then we'll remove the top element, which is 5 comma 1. It will go to the left. Right is already burned, so it will go to its parent. Parent call will happen. So 2 comma time 2, because this is time is equal to 1. This will be time is equal to 2. So this is burning. So at time 2, we'll remove this because it's the top. So 2 comma 2 will remove. It will check to its left. It will check to its top. Right is already burned. Left 4 comma 3, because it's time 2. So it will take time 3. Time 3, and this will also take time t is equal to 3. We put that also in the queue, 1 comma 3. And if it remove the top element from the queue, 4 comma 3, left, yes, left is there, so we add in the queue 8 comma 4, because this is time t is equal to 3. And then we'll remove the top element, 1 comma 3. 1 comma 3 left is already gone, parent is null. So right will take 3 comma 4, because this is 3. This will take time t is equal to 4. Then we'll again do the same thing, remove the top element. Top element is this. We'll check for left, nothing, right, nothing. Parent is already burnt, so will not burn it. We'll again remove the top element, 3 comma 4. 3 comma 4, left is nothing. Parent is already burnt. Right we have 7, so we'll put 7 comma. This is time 3. This is time 4. This is time 5. 7 comma 5. So after that we'll remove this and we'll return 5, because our queue is empty. We'll stop our algorithm and we'll return the max time. As we do all this, we'll also make a note of max time that we get, and we'll return that particular value. Said that already, we have to make a pair of values. First will contain the node, and the second will contain the time, and just will initialize all the given parameters. We'll make a hash map which will contain the parent child relation. So for 2 it will store 1, for 4 it will store 2, for 5 it will store 2, and correspondingly everything this hash map will store, and it will give the parent at over fun time complexity. So we'll make a queue, we'll add root. I'll explain you why. Because we are in this particular while loop, we are doing simple BFS, but here before adding the queue, we are also storing the parent for that current node. So if we take source null, which we have to find, because target is an integer value, but we need a node value for that. So I've taken a node source value and integer max for making the visited array. As I have said you, I've, as I have explained in the early section, that you require a visited array. So for that we take a max, and for node, for getting the node value of this, we'll make a node source which is null initially, and we'll add root to the queue initially. So we'll remove that element and we'll max the element and max the max and the data of that particular node. And this is just basic BFS. If you don't know, I'll highly recommend you to watch BFS and DFS and other traversal techniques, because it's very important in trees as well as in graphs. Traversals are very important. So if node dot data is equal to target, because we need the node value for this. So if the root dot data, as we know that the tree contains unique value, so this will always be a unique source. And after storing the before storing root dot left or current root dot left, we'll just make current root dot left parent as current root. So if we check here, this is current and this is current dot left. So we'll make current dot left parent as current node. So this is what I've written for left and this is what I've written for right. So we got all the parents and the visited array. We'll make visited array max plus one because we have to include seven as well. So we have to make seven plus one number of spaces for the visited array. All will be false first, and then if we visit any particular node, we'll make it true. We'll come to that. So first we have to make another queue for this BFS, which will find the time that we have to return eventually as the result. So as I've said, we'll make a pair value. So initially we'll add the source. Source is nothing but the target value only, but the node version of that, because we can only find left and right for a particular node and not an integer. So we'll give that node as the source and the time t is equal to 0, because it's always starting at time t is equal to 0. And this is very important. This I missed for the first time, I think, or I don't know, I don't remember, but this is very critical. I forgot this, but this is very important. Visited of target is true. What is because if we don't mark it as true, no, otherwise, if we don't mark this as true, when we go to the fourth node, again it will check for its parent. If it's not there, then again it will put it. So to avoid that, we have to mark it as true. This is also basic BFS approach. If you have done BFS or questions on trees, then you are familiar with this particular concept. And they'll make a result value which will just do the max of all the times, then we'll return that result. So we'll remove the particular current node, current pair, sorry. So this is a pair which will contain node value as well as time. So from this pair, we'll remove the node, extract the node, and we'll remove the time. We'll just max the time and the result, and then we'll return that. So we have to check for three values as mentioned in the question: left, right, and the parent. So here it's checking if this particular node contains a parent. For 2, it will be there 1. For 1, it will not be there. So this code will not be executed for 1. It will check if the parent is present and if the parent is not visited. This is very important. If the parent is not visited, then only we'll add that to the queue and we'll make it visited as true. This is also very common in BFS. We'll make a visited array and then we'll make it as true. In BFS it's very common. Similarly, we'll do for left call as well as the right call. If current dot left is not null, this is also very common in BFS, and it's not visited, then we'll add it and make it true. Similarly for right, and just will return the result value. Let's check. I've already submitted, so it will not give any error. So this is very good question because this gives an idea of how we can approach this kind of parent type of questions, because in trees it's not very common that we get questions related to parents. So this is a very interesting question and I highly recommend this question to everyone. Thank you. like, share, and subscribe. This is my third video for the day. Hopefully I maintain this consistency. Thank you.